Hello everybody, and this is going to be our video on exponential functions. So this is a little bit of a long one, so I'm going to try to move a little quickly with things just to keep the video from getting too long. But we do have a lot of little details to cover to make sure things are understood appropriately. So, well, let's just get to it. A function f of the form f of x equals a to the x power, where a is positive and not equal to 1, is called an exponential function with base a and exponent x. Okay, so what does this mean? What is all this saying? Well, this is just saying exponential functions are functions where your base is a constant and your exponent is a variable. That's all it says. But there's a condition on that base. That base has to be positive and not equal to 1. So let's make sure we understand why those two conditions are present. So the second condition is actually the quickest one. If we just look at y equals 1 to the x, that 1 to any power is just 1. So that would just be a constant valued function. That would be a pretty boring and uninteresting function and wouldn't describe the rest of the properties of the exponential functions that we want to describe, so we exclude that from consideration. Now, why does a need to be positive? Well, for a similar reason, we don't consider 0 to the x to be an exponential function, because 0 to any power is 0, unless x was 0, in which case it would be undefined. Okay, well, what about negative cases? Well, if the value of a was negative, say we had y equals -1 to the x power, then we could end up with some not good situations. For example, if x was 1/2, then the 1/2 power, hopefully we recall from algebra, is the same thing as the square root, and we'll go into more depth on that in a few minutes. But that would mean this is actually the square root of -1, but you can't take the square root of a negative number. That would not be a real valued number. So that doesn't really make any sense. So that would mean that this function would not be continuous for any fractional values 1 over an even number. So this causes all sorts of bad behavior, essentially. So what we're doing here is just excluding the cases that don't act the way we want them to act. We want these to be nice functions that behave in a very pleasant way, that make them useful for describing particular things in nature. And so these constant functions, they don't describe what we want to describe. And if we allowed negative bases, then we would have functions with a ton of discontinuities and poor behavior. So when we talk about exponential functions, those are our restrictions. The base has to be positive and cannot be equal to 1. Now let's take a look at this example 1. Evaluate the exponential function for the given value. F of x equals -3 to the 2x plus 1, and evaluate f of -2. Now a lot of times students get tripped up on a problem like this because they look at this and they go, well, isn't that base a negative? But this base is not a negative. The base here is 3. The negative is not part of the base, and this comes down to an order of operations issue. So when we look at this, this is actually f of x equals -1 times 3 to the 2x plus 1. And this exponent is only being applied to the base 3. The negative is not part of the base here. The exponent only applies to the 3. The negative is applied after, because in the order of operations, exponents come before multiplication. So this multiplication by -1 occurs after the base has been evaluated, this exponent. So this is still an exponential function. It's a transformation on an exponential function, but it's still exponential because the base is still a positive number other than 1. Okay, so with that being said, let's evaluate f of -2. Get -1 times 3 to the 2 times -2 plus 1. That's -1 times 3 to the -4 plus 1. That's -1 times 3 to the -3rd power. And that's -1 over 3 cubed, right? So when we have a negative exponent, that's the same thing as the reciprocal. Again, we're going to go back over those algebraic exponential rules just to make sure we understand them really well here. But for now, let's just recall that a negative exponent is a reciprocal. So this is really negative 1 over 3 cubed, which is 27. So that's f of negative 2 there. Okay, so let's take a look at 3 key facts about exponential functions. First of all, exponential functions are defined for all real numbers x. Right? As long as we've got this condition where the base is positive and not equal to 1, any number you plug in for x into your exponential function is going to work. Also, the graph of an exponential function is a continuous unbroken curve. So all the laws about continuity regarding limits, things like that, those all apply. And the rules of exponents apply for any real numbered exponents in positive bases. So on that topic, now let's go ahead and review those rules of exponents. So we've got a list of 8 rules here, and we're just going to go through each of these, and we're going to look at some, for some of these we're going to really justify properly. For others, we're going to look at some like key examples to explain why the rules work the way they work. So for this first one, we have a to the x times a to the y equals a to the x plus y. Okay, so what this says is if I have a product of 2 exponential functions with the same base, then I can just add their exponents together. So why can I do that? Well, we have to think about what an exponent means. At its most basic level, an exponent means repeated multiplication. So when I say a squared times a cubed, a squared means a times a. And a cubed means a times a times a. So if I ask how many times am I really multiplying a together, well, it's 2 plus 3, which is 5. This is a to the 5th. So if exponents count the repeated multiplication, then if I am multiplying by that thing more times, I just need to add the number of times that they've been multiplied together. Okay, next, a to the x to the y power equals a to the x times y power. So, for example, if we look at a squared cubed, a squared means a times a, and we're cubing that, which means we're taking a times a and multiplying it by itself 3 times. So what do I have? I have 3 groups of 2 products of a. 3 groups of 2 is 6. That's a to the 6th power, right? So that's really what this is saying. You're multiplying a in y groups of x. So that's a to the x times y, right? Just like this is 2 times 3 is 6. Okay, now we've got a times b all to the x power equals a to the x times b to the x. So this rule essentially says we can multiply in any order. So what do I mean by that? If I have a times b squared, that's really a times b multiplied by a times b. But I can multiply in any order, so I can multiply the 2 a's first and the 2 b's second, and that gives me a squared times b squared. So that's all this law says, is that you can multiply in any order. So if you're raising both of these products to the same exponent, you can split that exponent up across the 2 expressions. Okay, now we look at a to the x divided by a to the y. That's a to the x minus y. Okay, so why is that? Well, if I have a cubed over a squared, that's a times a times a divided by a times a. And as long as there are only products here, remember if there was a plus or a minus, we couldn't do any of this. But as long as we have things that are just factored products, we can cancel each matching factor on the top and bottom. So for each factor in the denominator, I was able to remove 1 factor in the numerator. So that's 3 factors minus 2 factors leaves me with 1 factor, a to the 1st power. So that's why a to the x over a to the y can be written as a to the x minus y. Okay, now we look at a to the 0 equals 1. So this is a bane of many a student's existence. Why in the world is the 0 exponent going to give you 1? Well, hopefully at this point all of these previous rules make sense and we understand why these rules are what they are. And it should be clear that any mathematical rules have to be self-consistent, right? If they don't all work with one another, if they contradict each other, then they don't make sense. So let's take a look at rule 4 here. but we're going to consider a to the x divided by a to the x. And I know that any number divided by itself is 1, but Rule 4 says that a to the x over a to the x is the same thing as a to the x minus x. But x minus x is 0, so this is a to the 0 power. Okay, so essentially when we say a to the 0 equals 1, we're basically saying any number divided by itself equals 1. That's what a to the 0 equals 1 means. Okay, so let's go ahead and look at these next few properties here. Now we've got a to the negative x equals 1 over a to the x power, which is the same thing as 1 over a all to the x power, because 1 to the x is 1. So how do we get this law? In other words, negative exponents give us the reciprocal. Well, that actually comes from combining laws 4 and 5. So I know that 1 is the same thing as a to the 0. So 1 over a to the x is the same thing as a to the 0 over a to the x. And Rule 4 tells us we can subtract those exponents, a to the 0 minus x, which is a to the negative x. Okay, number 7. Here we've got a to the 1 over q equals the qth root of a. So let's take a look at the square root. Right? With the square root, there's implicitly a 2 here. We just don't write it. So we've got the square root of a. And the definition of the square root says the square root is the number that multiplied by itself equals what's inside. So by definition, if I multiply the square root of a times the square root of a, I get a. Now, what about a to the 1/2 power? Well, if I take a to the 1/2 power times a to the 1/2 power, 1/2 plus 1/2 is a to the 1st power. So, those are the same thing. Let's take a look at the cubed root then. Well, the cubed root means the number that multiplied by itself 3 times gives you what's inside. So if we look at a to the 1/3 power and multiply it by itself 3 times, what do we see? 1/3 plus 1/3 plus 1/3 is 1. That's a to the 1st power. So essentially, the qth root and the 1 over q power are just describing exactly the same. What number multiplied by itself q times gives you what's inside, right? So they mean the same thing, and hence those notations are interchangeable. But because we're used to working with certain notations in certain contexts, sometimes we prefer a radical notation, sometimes we prefer the exponent notation. Okay, and Rule 8 is just a combination of Rule 7 and our previous rule about exponents raised to a power. So if I take a to the p over q, I can rewrite that as a to the p times 1 over q. And that's a to the p to the 1 over q power. Right? That's the same thing as rule number 2 here. A to the x times y equals a to the x to the y power. But the 1 over qth power is the qth root. So this is the qth root of a to the p. So in other words, a to the p over q is equal to the qth root of a to the p. Okay, so hopefully going through the justifications and the understanding of why these exponential function rules are what they are will help you remember them a little better. Typically, find that students sometimes struggle to remember some of these rules, and usually once they understand where the rules come from, those rules stick a lot better in their memory. All right, so with that, let's go ahead and get to an example. Find a function of the form f of x equals c times a to the x that contains the two given graph points, 1, 1, and 2, 15. So the key thing to make sure you understand is that a point is a set of a paired x and y value that satisfy the equation for the function. So that means that when I plug in x equals 1, I should get y equals 1 here. When I plug in x equals 2, I should get y equals 15. So this is asking me to figure out what this function really looks like, what c and a are, knowing what inputs correspond to which outputs. So if we take a look at 1, 1, and I plug in this x and y value, I get y is 1 equals c times a to the first power. And if I plug in the point 2, 15, I get 15 equals c times a squared. So now I want to solve this system of equations, right? I have two unknown variables. I have two equations. So I want to solve for a and c. So there's a number of ways we can do this algebraically, but what I'm going to go ahead and do is solve for isolate c first. So I'll divide a across on my first equation. I get c equals 1 over a, and then I'm going to plug that in to my second equation, which gives me 15 equals 1 over a times a squared. And a squared divided by a is just a to the first power. So that tells me that a equals 15. And now I can take that result and plug it back into here. And that gives me c equals 1 over 15. So my final answer here is that f of x equals 1 over 15 times 15 to the x. Okay, so that's it, right? Just plug in your 2 points, you get a system of 2 equations, isolate one, plug it into the other function, and then that lets you solve one of your unknowns, and you plug that back into the other expression, and now you have both of your unknowns, and now we can write out our function. Okay, so let's take a look at another example. So this is a similar one. Find a function of the form f of x equals a to the x plus b that contains the two given graph points. So the other one was c times a to the x. This one is a to the x plus b. So slightly different algebraically. Let's go ahead and start with this first point, 0, 2. So my y value is 2. I get 2 equals a to the 0 power plus b. A to the 0 power is just 1, so this is 2 equals 1 plus b. So I actually can solve for b immediately here. Subtract the 1, and I get b equals 1. So that's kind of nice. I didn't need both equations to solve for b in this case, just because that 0 exponent takes care of a immediately. Now if I take a look at 2, 10, y is 10, x is 2. And now let's plug our value for b into this equation. We get 10 equals a squared plus 1. I subtract the 1. I get 9 equals a squared. And so if I take the square root of both sides, what do I get? I get a equals plus or minus the square root of 9. But this is really, really important. We already know that a has to be positive because it's an exponential function. So that means I can ignore that negative root. I got 2 possible answers, and the real answer is just the positive root 9, but radical 9 is, of course, 3. Okay, so that's it for example number 3. Now we're going to talk about graphing transformations of exponential functions. So all of the graphing transformations of exponential functions, there's not a whole lot to say here because it's exactly the same as graphing functions in general. So when we talked about general principles of graphing functions, all of those general principles apply exactly the same here. So we're going to kind of go through them quickly. The difference is the starting point. How do you start with your graph? And so one of the mistakes that students make is they often will try to plot a bunch of points. They think that graphing means plot as many points as you can, and then that's the graph. But that's a really inefficient way to graph functions. Instead, what we want to do is graph a few key points, and then use the properties of the functions to fill out the rest of the shape. So in the case of exponential functions, the key points are going to be the x values -1, 0, and 1, and that's just because they're the easy ones to evaluate, and that's typically the case. Our key points that we choose for building our shape of our graph are usually the values that are really easy to evaluate. So what do I mean by that? Well, we know that a to the 0 is 1. So if I take a greater than 1, so for any a greater than 1, and I plug in 0, I get 1. There's my point on the graph. Now if I take a to the first power, that's just a. So when I plug in x equals 1 here, I get a on my graph. And if I take a to the negative first power, I get 1 over a. So that's down here. If a is bigger than 1, 1 over a is smaller than 1. So when I plug in x equals -1, this is what I get. And if we take a number bigger than 1 and we raise it to larger and larger powers, we know that our graph is going to grow, right? Like 2 cubed is 8, 2 to the 4th power is 16, so forth and so on. And I know for the negative exponents, I'm going to get 1 over a to that power, so those values are going to be approaching 0. But we can never get a negative value, right? If a is a positive number greater than 1, positive exponents give me positive numbers. When I get 0, I get 1. When I have negative exponents, I still get positive numbers. 1 divided by a positive number a is still positive. So this function is always strictly positive, and that tells us that we have a horizontal asymptote at y equals 0. That's just the x-axis. Okay, so with that being said, once we understand the basic graph and we know how to graph these 3 key points, then all of the transformations are going to work the same way as they do for every other graph. So for a to the x minus h plus k, we look at our input, x minus h, we set it equal to 0 and solve it. That's x equals h. So this is a shift right by h. And then plus k shifts us up by k. So what do? We take each of our 3 key points, we shift them over by h and up by k. And if our whole graph shifts up by k, then our horizontal asymptote has to shift up by k as well, right? So now we have y equals k as the horizontal asymptote. So when we're talking about the exponential functions, these horizontal asymptotes only move if the graph moves up or down. So you can always easily find the horizontal asymptote by keeping that in mind. Now, of course, if we have f of x equals a to the negative x, that's a reflection about the y-axis. So you just take your 3 points and flip them over the y-axis, and you get this graph. And if I have negative a to the x, that's taking the previous function a to the x and making the whole thing negative. So you take each of your y values and plot them below, mirror image over the x-axis, and that's that. So with all of that being said, let's take a look at 2 quick properties. The limit as x goes to infinity of a to the x equals infinity, and the limit as x goes to negative infinity of a to the x equals 0. We've actually already talked about why this is the case. When we look at this graph, if I trace towards the right, the graph keeps going up. So that means that when x goes to infinity, so does the y value go to infinity. And when we go to the left, the y value goes down to 0. So when x goes to negative infinity, a to the x goes to 0. Now keep in mind, everything that we just said was for the case that a is greater than 0, or greater than 1, I should say. But exponential functions can also have the base be between 0 and 1. So we're just going to sketch a quick graph of the basic exponential function in the case that a is between 0 and 1. So if a is between 0 and 1, that would put a somewhere like this, which means 1 over a would look more like this. So now when I plot my points, nothing really changes conceptually, right? A to the 0 is still 1. And a to the first power is still a. And a to the negative first power is 1 over a. The difference is that because a is now between 0 and 1, those y values essentially flipped place on our graph. So if your exponential function has a base between 0 and 1, then your parent graph is just going to look like the mirror image of the regular a to the x function. Or I say the one when a is greater than 1. It's not really regular, it's just the one where a is bigger than 1. Okay, and from this graph we see that, hey, those limits basically switch places. Now when x goes to infinity, the limit of a to the x is 0. And when x goes to negative infinity, the limit of a to the x is infinity. All right, that's it for that one. Now let's move on to an actual example. Start with the basic graph of the exponential function f and use transformations to sketch the graph of g. State the domain and range of g and the horizontal asymptote of its graph. So when we're talking about exponential functions, the basic graph always means y equals a to the x. So in this case, our base is 4, so our basic graph is just y equals 4 to the x. And so we're going to graph that. We're always going to graph that by starting with our key points. All right, when x is 0, 4 to the 0 is 1. When x is 1, 4 to the first power is 4. And when x is negative 1, I get 1/4. That's it. Plot those 3 points, connect the dots. That's your basic graph. So your goal should be to be able to draw the basic graph for a parent function within about 10 seconds. That really shouldn't take you any time. You're just looking at x equals negative 1, 0, and 1, and then sketch the shape of the graph between them, and remember that your asymptote is always going to be at y equals 0. Now, this graph is going to shift to y equals 4 to the x minus 1, and that's just a shift down by 1. So if I'm shifting down by 1, my asymptote that was at y equals 0 is now going to be at y equals negative 1. And all of my points are going to drop down 1 with it. All right, so that's our graph, and now we just got to answer the questions here. State the domain and range of g and the horizontal asymptote of its graph. The domain is easy. We can still plug in any number into this function. It will still work. So it's still negative infinity to infinity. Now the range, we have to notice that because our graph shifted down, our outputs will now look like outputs from negative 1 to infinity. And our horizontal asymptote shifted down with our graph, so that's now y equals negative 1. All right, so that's it for example 4. Let's go ahead and move on to another graphing example. Okay, so first recall that the number e, it's just a number that's approximately 2.72. So we're going to discuss this number more precisely later in the video, so you have some background as to why we care about the number e, why we gave it a special name. But we'll wait to get to that, and for now, we'll just go ahead and graph an exponential function that's got base e and work on the graphing. So we start with our basic graph, y equals e to the x. So this works exactly the same way as graphing our other functions, our other exponential functions. All right, but I'm going to mark 1, 2, 3, but since e is about 2.7, I'm going to put a little mark for e, and then a little mark for 1 over e down here. That'll just make things a little easier for me. And now we plot our points. When x is 0, I get 1. When x is 1, I get e. When x is negative 1, I get 1 over e. connect my dots. And there's my graph for y equals e to the x. Now we have a bunch of transformations in here, so now we have to actually think carefully about our order of transformations. Remember that there is implicitly a parentheses here, so we always do what's inside the function inside the parentheses first, and then we look at PEMDAS, right? So what's inside this exponent here? We've got multiplication by x and then subtraction, and multiplication comes first. So we go, okay, let's look at y equals e to the negative x. And when we make x negative, that's a reflection over the y-axis. And again, I'll make all the same marks. Now I'm going to mark the same spots for e and 1 over e, but I'm not going to relabel them every time, because that'd get a little redundant. All right, so I flip those points over the y-axis, and then connect my dots, and bam, I'm done. That's y equals e to the negative x. And now let's do another transformation. Y equals e to the negative x. Now what's the next thing inside the exponent? Now it's the subtraction. Y equals e to the negative x minus 3. And remember, we're always going to take our input, set it equal to 0, and solve it. And here we get x equals negative 3. So that tells us this is a shift left by 3. So that means I'm going to basically take all of my points and just move them over 1. Or over 3, I should say. One, two, three. So that top point goes there. 1, 2, 3. And this one started here. So 1, 2, 3. So our graph should look basically like this. Okay, so 3 transformations down. Now we've done everything inside the function. Now we move outside the function. And this is a multiplication by negative 1. So multiplication comes before the addition here. So we're going to go to the y equals negative e to the negative x minus 3 graph. And here I'm taking the previous y value and making the whole thing negative. So this is a reflection over the x-axis. So now, since I'm going to be reflecting over the x-axis, I'm going to take those orange marks for 1 over e and e and make them the negative 1 over e and negative e. Other than that, I just take my points, flip them down. And at that stage, all I've got left to do is one more transformation, and that's this plus 4 here. And of course, that's just a shift up by 4. So here, I'm going to move my orange marks up by 4 as well. So this one is at negative 1 over e. If I add 4, that's going to be just less than 4 here. And this one was at negative e, so when I add 4, that's going to be just under, let's see, 1, 2, 3, 4. It's going to be just under here. And we'll move our points accordingly. So we go up 4 from this point, which was at -2, -1/e. So that goes up to here. This one was at -3, -1. So that's going to go up to here. And this last one moves to here. And keep in mind, our asymptote was the the x-axis. So it's moved up 4 to y equals 4. So finally, we can state our domain. That's still -infinity to infinity. Our range, which now is 4 and below. So that's -infinity to 4. And our asymptote is y equals 4. So I realize that it's definitely possible for students to do all of your transformations at once and get your resulting graph correct. But when you're initially practicing this stuff, you will be much less prone to mistakes if you always do these transformations one at a time. It's going to make it to where, when you're working on tests, things like that, you're much less likely to misinterpret some of the transformations. Because remember, this order matters. So if you don't do the reflections and the shifts in the proper order by using this order of operations, then it's going to make it more likely for you to just make a little mistake and interpret something wrong and have the wrong graph. Okay, so now that we're done with that, let's go ahead and move on to talk about interest formulas. So we're going to start by talking about simple interest and compound interest, and then move on to continuous compounding interest. Now, the main reason I'm actually going to talk about interest is to motivate what I said earlier, which was about the number e. Why in the world do we care about this number e that's 2.72-ish? So there's many applications actually that relate to this number, but I think the easiest one for students to see early on is to take a look at interest. So that's the main reason we're looking at interest here. So the simple interest I on a principal P at a rate R expressed as a decimal per year is given for t years by I equals P times RT. So this is the idea that you are charged interest one time based on how long you're borrowing something. So let's say a buddy says, hey, I'll lend you $1,000 for 2 years at 10% per year. So that says, well, okay, 10% per year, that's 20%. So the interest you're paying is 20% times your principal of $1,000, right? But that's not the way most interest is charged. Interest in general is charged on a month-to-month basis, or a periodic basis at least, meaning that you collect some interest and that interest gets put back into the amount that's owed, so that any new interest is added on top of that amount. So that leads us to the compound interest formula below. The amount earned after t years, A, so the amount is A, using compound interest is given by A equals P times 1 plus R over N to the NT power, where P is the principal, R is the annual interest rate, and N is the number of times interest is compounded each year. So this formula sometimes, or can at least initially seem like a bit of a mystery, like where in the world do they get this formula come from? But it's actually just a little bit of algebraic manipulation. So what I'm going to do is kind of lay out an example of a compound interest problem, and we're going to work through it the long way without using the formula to see why the formula makes sense. So let's consider some simple cases, right? So we're just going to use some very simple values here for R and N. So for R, the interest rate, let's say R is 10%. So that's just 0.1. And let's say that N is the number of times interest is compounded per year. Let's say we're compounding monthly. So that's 12. So we're getting interest every month. Okay, so then one of the things we should understand is that n times t then is actually the number of times interest is compounded. N times t is the number of times interest is compounded, right? If you're doing 12 times per year and you do 2 years, that's 24 times that you are compounding the interest. Okay, so let's just go ahead and take a look at what happens after 1 month. So we'll say you've got a savings account, you put your principal in, and at the end of that month, the bank says, hey, you know, we're giving you 10% interest. You'll never get 10% interest on a savings account. But just hypothetically speaking, for ease, let's say they say, we give you 10% per year, but how much do I get per month? Well, they're not going to give you the 10% per month. They're going to give you 1/12 of that. So that means that R divided by N is the interest, in this case, per month. So the bank says, hey, 1 month has gone by. We're going to go ahead and give you that 0.1 divided by 12 times the principal. So this is the portion of the principal that we're going to add to your amount. You've already got your original principal, and we're going to add this bit extra on top of it. So let's just factor that out. That gives us P times 1 plus 0.1 over 12. Done. Now what happens at the end of 2 months? So 2 months goes by, your bank has to pay you some more interest. Now you've already got this amount in, right? The first month has passed. For this next month, you've had this amount in the whole time, which was P times 1 plus 0.1 over 12. And now the bank says, hey, we're going to give you interest again, but the interest we're going to give you is going to be on the new amount that you've had for this whole month. So we're going to take that new amount and multiply it by 0.1 over 12. Okay, well, what do I notice? Well, I've got the same product here, P times 1 plus 0.1 over 12 plus P times 1 plus 0.1 over 12 times this. So I can factor this thing I've underlined out of both, and I get P times 1 plus 0.1 over 12 times, and when I factor that out, I get left with a 1 on this side plus 0.1 over 12. Oh, well, look at that. That's the same expression here. So this is really P times 1 plus 0.1 over 12 squared. So what do we notice? 2 is the number of times the interest has been compounded. We've had 2 months, it's been compounded 2 times. And otherwise, what does this look like? P times 1 plus R over N to the NT power, right? P times 1 plus R over N to the NT power. So that's all this compound interest formula is it's a shortcut for working out what we just worked through the long way. That's it. So that's how we use compound interest. Now, again, the reason I wanted to talk about compound interest was to think about, well, where does this number E come from? So the definition for E is actually the limit as h goes to infinity of 1 plus 1 over h to the h power. So this expression, 1 plus 1 over h to the h power, approaches this infinite decimal that looks like 2.7183. Now, it's actually pretty tricky to show that. To show that this thing actually approaches a fixed number and to compute that number to any accuracy is a bit beyond the techniques we have. In Calculus 2, you'll have the techniques you need to do that kind of work. But we don't really have those techniques here. So we're just going to cite that fact and use that fact. But I do want to show you why we've defined this number as E, why we gave this expression a special name when h approaches infinity. And it's all about this continuous compounding interest formula. So the continuous compounding interest formula is A equals P times e to the RT. You might have heard it as the PERT formula. So the question is, why does this make sense for continuous compounding interest? Well, as we hopefully realized from the previous example, the more often you compound interest, the more money you get. So if you can compound interest every second, you're going to be making way more money than you did just every month. And if you could imagine compounding interest every instant, how much money would you make? Well, of course, banks, when they're charging interest, they want to make the most money they possibly can, so they tend to charge continuous compounding interest. So how do they do that? How do they figure out a formula for continuous compounding interest? They took a limit, right? So they looked at the formula for periodic compounding interest, P times 1 plus R over N to the NT power. And they said, what happens as the number of times we compound our interest goes to infinity? What happens to it then? So what we're going to do, notice this expression for E has 1 over H in this same spot here. So what we're going to do is a little substitution. This is a pretty clever algebra trick for dealing with this strange limit situation. But what we're going to do is just replace the expression R over N with 1 over H. Okay, but if I'm going to do that, how do I deal with this exponent? Well, first of all, I can't be talking about a limit as n goes to infinity anymore because I've replaced this expression with n. But if n goes to infinity, r over n is approaching 0, and it's going to act the same way as if h was going to infinity, because then 1 over h is going to 0. So we can think of this as a limit as h goes to infinity. But how do I deal with this exponent here? Well, I'll just solve this equation for n and substitute it back in. So I multiply n across, and I multiply h across. I get n equals h times r. And so when I substitute that into my exponent, I get h times rt. And now what do we see? The limit as h goes to infinity of p times. So what I'm going to do now is just apply my limit law. Up here I've got the product of h times rt. So I'm going to write this as to the power of h all to the rt power. And what did our definition for e say? It said this 1 plus 1 over h to the h, when h goes to infinity, this is approaching e. So that's our PERT formula. So, in other words, we actually already knew, hey, 1 plus 1 over h to the h, it's approaching some number, right? So we gave it a name. We said, hey, this is approaching some number. This comes up a lot in these interest formulas. It also comes up in natural applications like population growth. Has a very similar derivation of formulas, or radioactive decay. So what did we do? We said, hey, let's just go ahead and give this number a special name. We'll call it E. That way we don't have to have this complicated limit expression. We can say, hey, this number is like roughly 2.7183, so we'll give it a name. We'll call it E, and that lets us simplify this formula for the continuous compounding interest. And that's basically it. That's where E comes from. So with that being said, let's go ahead and take a look real quick at a summary for natural exponential growth and decay. So as I said, when we talk about population growth or radiation decay, things like that, they behave in a very similar way to interest rates actually in terms of the mathematical computations. So our PERT formula is essentially the same formula. So for k being positive, exponential growth is given by a of t equals a naught times e to the kt. So that looks just like PERT, but because we're not talking about principal, we just renotated it as a naught, meaning the initial amount of something. And k here is the relative rate of growth or decay. So for exponential decay, that's just when your exponent is a negative, because then your graph is going down instead of going up. All right, and let's go ahead and take a look at an example. The temperature T in Celsius of hot cocoa at time t, after its removal from the stove, is given by big T equals 20 plus 75 e to the negative 0.3 t. Find the temperature at each given time. So we'll start with t equal to 0. So capital T evaluated at 0 is 20 plus 75 times e to the negative 0.3 times 0. That's 20 plus 75 times e to the 0, right? And e to the 0 is 1, so this is 20 plus 75, which is 95. Okay, and now if we take a look at B when t equals 25, we get 20 plus 75 times e. And instead of writing negative 0.3, I'm going to write negative 3/10 because it's easier to work out with fractions, times t, which is 25. So we get negative 75 over 10. And negative 75 over 10 simplifies to negative 15 halves. Now, if you needed a decimal, you could plug this into a calculator and get a decimal answer for it. I'm going to go ahead and leave it as is. Okay, now, after a long time, so when we say the phrase after a long time, we're asking what is the limit. So we're taking the limit as t goes to infinity of our temperature function. Now this seems like it's pretty tricky, but actually if we do a little bit of algebra rewriting here, this actually is pretty easy to figure out. So since I've got a negative exponent, I'm going to rewrite this as e to the 0.3 times t. And now we're just going to break this down piece by piece. So since t is approaching infinity, that means this exponent is approaching infinity. But I know from my exponential function graphs that if the exponent is approaching infinity, then the whole exponential function is approaching infinity. And I know from limit behaviors that if I have a fraction and the numerator is a fixed number and the denominator is approaching infinity, then I know the whole thing there is approaching 0. So 75 over this exponential expression is going to 0. This whole thing works out to 20 plus 0, which is 20. So in other words, actually, what this tells you is that 20 is the room temperature, right? If you think about that, you take your hot cocoa off the stove, what's it going to do? It's going to cool down until it hits room temperature. So 20 here is the temperature of the room, and this limit is just telling you, hey, as that cocoa sits long enough, eventually that hot cocoa cools off until it hits room temperature. Okay, well that's it for this section. Thank you for watching.